Is it on? Oh, okay. All right, time to start. Some people asked good questions yesterday after class, and so I'll first just address some of those questions so everyone can hear the answers to them. So in the derivations yesterday on policy gradient methods, I didn't show all of the details because a lot of this, you have a lot of these calculations where you're just moving around expectations. So there's, then I realized, well, it turned out I didn't show this derivation for why the baseline why you still get an unbiased estimator when you introduce a baseline. And that particular fact is pretty important, so I'll just go through the derivation of that right now. So recall that we have the, let's just look at the policy gradient formula. We have this expectation over trajectories, sum over time steps, and we have this sum of returns minus baseline. And I claimed that this baseline doesn't actually affect the expectation of, it doesn't affect this expectation here. So you can set the baseline to whatever you want and it's not going to affect the expectation. It'll just change the variance. So that's the claim I made yesterday. Here's the derivation for it. So just consider one of those terms, grad log probability times the baseline. These are the terms we introduced by adding a baseline, and I'm going to show that the expectation of this term is 0. So what you do is you first break up the expectation, break up the variables that you're integrating over in the expectation. So you've got the variables that get sampled before a sub t, and the variables that you get that get sampled after or equal to a sub t. So those are our two nested expectations here. Then the baseline the baseline gets sampled before all of these variables, so we can move it outside the expectation. So all we're left with, all that we're left with inside of the expectation is this grad log probability term. Okay, and this expectation, the only relevant variable is a sub t. That's the only random variable that gets sampled after. That's the only random variable that gets sampled that you need to sample to compute this grad log probability. And then this expectation of grad log probability equals 0. And the reason for that is, let's say we just consider the expectation of 1, which is, and if we take, so that's obviously just the constant 1. And if we take the gradient of that and we write down the estimator for the gradient of that expectation, we get the expectation of grad log probability. So we're just writing down this identity that grad expectation of 1 equals the expectation of grad log probability. So obviously this term, expectation of grad log probability, is 0. So yeah, going back here, we see that that gives us this last equality here. So we see that the expectation is 0. So that's why the baseline doesn't affect the policy gradient. And then someone else was asking, why does the baseline reduce variance? And why do we want to set the baseline? Why do we want to choose a baseline that approximates the state value function? Why does that reduce variance? So I'll give a sketchy derivation of this. You can find a more precise derivation in several papers. If you're interested, I can point you to one of the papers. But for a sketchy derivation, let's derive it by just considering the formula for the variance. So let's just look at one of these terms. So we're interested in variance of grad log probability of AT given ST times some estimator of the returns. Let's call it, let's just say R sub t minus baseline of ST. So we're interested in the variance. The variance, this doesn't tell us exactly what we want to know. We want to know the variance of this whole estimator, which involves a sum over time steps. And here we're just considering one time step. And it's not generally true that the variance of the sum of two random variables equals the sum of the variances. But let's just ignore that and try to look at, because this is just for the sake of intuition, and let's just look at what the variance of this term is. So as I showed before, okay, so in general, when you have some random variable, the variance is just the expectation of the variable squared minus the squared expectation. So when we want to write down the variance of this term right here, we've got the expectation of this term squared minus the squared expectation. But the squared expectation doesn't depend on the baseline, because as we just saw, the expectation doesn't depend on the baseline. So what we want to do to minimize this variance is just to, well, the only term we care about is the expectation of this quantity squared inside the expectation. Oh, can everyone see what I'm writing on the board, by the way? Okay. You want me to use black marker? Okay.
Don't use the here on the left.
Okay, got it. So we have expectation of grad log probability of AT given ST times our returns minus baseline. And this whole thing inside is squared. This marker is kind of bad, unfortunately. Let me try another one. Okay, so we've got this whole quantity squared. Now, here's the step. Here's the leap of faith number 2, or the kind of BS step number 2. Bachelor of Science step number 2. Not good enough for the PhD, but this is okay if you're just an undergrad. So the expectation of okay, we can write this. Let's just move our parentheses around. So we have the grad log probability squared times the return minus baseline squared. So the argument we're going to make is, well, when you have two independent variables and we're taking the expectation of the product, if they're independent, then it's also true that the expectation of the product is the product of the expectations. So that's not true in general, but it's true if they're independent. So let's just assume that these two random variables are independent. So then we've got expectation of, can everyone see what I'm writing on the board? This marker is kind of bad. Let me see. Those are even worse, I heard. So okay, let's just go with, I kind of felt like the red marker was better though. So let's see. Okay, this blue one is really good.
John, I want to see.
You have a, okay, could you toss it? Let's see. Oh.
Is there a blue marker up there?
Oh yeah, I've got a really good blue one.
That one.
Oh yeah. Okay. So we've got grad log probability squared times our reward minus or return minus baseline squared. Okay, this term doesn't depend on our baseline. And we're just trying to make this as small as possible. So clearly, we should set the baseline to be as close as possible to the expectation of this term, because if you have the expectation of some variable x minus, if you have some quantity like this, you can rewrite it where b is a constant. You can rewrite it like expectation. You can let's see, write it as variance of x plus x plus expectation of x minus b squared, I think. Is this right? So, OK, but the point is that we have this, OK, we want to make this quantity as small as possible, so we set the baseline to be the expectation of this random variable here. OK, so that's the sketchy derivation. Or it's just sort of an intuitive explanation of why you want the value function to be approximately equal to the expected return. Yeah?
I think this is a great way to build the intuition for it. I have a question.
Yeah.
So you showed how you can reduce the variance of the estimate of the gradient by subtracting from the reward. Can you subtract a different value for every coordinate of the gradient?
Oh yeah, so so you're hinting at the optimal baseline formula. So this it turns out that there's actually a better a choice of baseline that actually does minimize the variance, and it ends up being different for every parameter. So here we're trying to estimate a vector. The policy gradient is a vector, and we can write down a estimator for every single component. So it's grad log probability with respect to this one component times returns minus baseline. And OK, you can go through the real derivation for what the optimal baseline should be. And the way you do that is you just write down the variance and you take the derivative with respect to the baseline. And you go through this calculation and you find that it's actually going to be different for every coordinate. And I'll just write down what the actual formula is. This is not a formula that you ever end up using in practice, because the formula where you just, setting the baseline equal to the value function is near optimal, and it's as good as optimal for all practical purposes. But let's just write down what the actual correct formula is. So it ends up being it ends up being that OK, we have the let's say the ith element. So our estimator, our policy gradient estimator for the ith element is going to look like this. So this is our estimator, and variance is minimized when we can choose a different baseline for every component of the policy gradient, and it turns out the optimal one equals what is it, grad. It's like a weighted average of the returns, where you weight by the grad log probability squared. So you take the expectation of grad log probability squared times r over the expectation of grad log probability squared. So it's the weighted average instead of being the just the mean. And you can think about if to get a little more intuition of why using the state value function is almost optimal, you can just think about for what distributions does this weighted average almost equal the average, the unweighted average. OK, so that's what's going on with optimal baselines. Any questions?
So the situation when these two are equal is when you have a uniform?
It doesn't even have to be uniform. I think, let's see. I would have to think about it a little bit. Let's see. Yeah, let's talk about that afterwards. Yeah.
There's a question.
Oh yeah.
Here I think BI is like the optimal control variable.
Yeah.
That's how it's been tuned, but in the original case it's not, right?
Okay, right. Yeah. So.
Because if you just minimize the
Yeah. Okay, yeah, so the question was, this baseline is what you get when you look at the optimal control variate. And yeah, that's correct. So control variates are another general statistical technique to minimize the variance of estimators. So if, yeah, this is actually, it turns out to be a special case of the control variate method. So if you know about control variates, that's what it is. And this, so this baseline is optimal, and it's a vector. You get a vector of baselines instead of just a scalar. But it turns out the other, the approximately optimal baseline we showed yesterday or 2 classes ago with the state value function is good enough. Okay, that's one thing I wanted to mention. And also, I was making this claim about, oh, it's in the next lecture. Let's see. Oh, about MPC, I was making this claim. I was making this claim that when you do, you find the discounted, when you do policy gradients with discounts, that's related to MPC. Because if you're at the optimum, if you're at the policy where this discounted policy gradient is 0, then that means you have the optimal policy according to the gamma discounted return. So that's the claim I made, and I was saying that I was making the claim that if the policy gradient with the discount gamma equals 0, then that means that you must have q pi gamma equals q star gamma, and where q star gamma is just the q function of the optimal policy, and that's true because if it's true that if you have that A equals arg max of q of SA, that means that that means that when you do a, or actually let's say if pi of S happens to equal the argmax over actions of the Q function of this policy, that would mean that when you do the backup, the Bellman backup, then you get the same Q function that you had before. And that would mean that Q must equal Q star. Actually, I'm realizing that this will make more sense after the next few slides from this class. So if this didn't make sense, which it probably didn't, don't worry about it. It'll hopefully make more sense pretty soon. OK, let me go. So let's see. OK, so this class is on. So first, let me recap the last 2 classes and say how this one relates to it. So 2 classes ago, we talked about MDPs and 2 algorithms for solving for optimal policies in MDPs, policy iteration and value iteration. And these algorithms could only be applied if you know all of the parameters of the MDP. So if you completely know all the transition probabilities, you can apply these 2 algorithms. And they also only work when you have a finite state and action space. So let's, OK, so then last class we talked about policy gradient methods where you don't have to know what the transition probabilities are. So you can apply it in a more general situation. So this class, we're going to talk about some methods that are actually more similar to what we were doing 2 classes ago. So we're going to talk about how to use value function based algorithms to solve for the optimal policies. And but we're going to talk about methods that you can apply when you don't know all the parameters of the MDP. So this is called model-free reinforcement learning because it's not assumed that you know the model of the system. And I'm going to talk about a class of methods that are model-free reinforcement learning methods, which use value functions, which center around value functions, and they're related to value iteration and policy iteration. In particular, we're going to talk mostly about value iteration in this class. So first, let's just review these definitions of value functions from the previous class. So on the top, so these are just, here we're just going to review the definitions of the value functions that you get for a fixed policy pi, as opposed to the optimal value function. So the Q function is this expected discounted sum of rewards where you condition on the first state and the first action. The state value function V, you just condition on the first state. And the advantage function, you take the difference. So you can write down, 2 classes ago we talked about the Bellman equation for the value function. And so we wrote that an equation that's like V of S equals expectation of, or max over actions of expectation of reward plus gamma times next value. So you have a, so the Bellman equation is just a consistency equation on the value function. So we can write down a similar kind of consistency equation for the Q function just using its definition. So since the Q function, yeah, so so it looks like this, where you look at, you have the first reward plus the Q function at the next time step. So this is the equation that Q pi should satisfy, and that's just the top formula looks one time step into the future, and we can also write it with looking k steps into the future. So here we can expand. So we can expand it out one more time step. I mean, if we just take if we take this formula and we substitute in the definition of Q again, but starting at S1 and A1, then we expand it out and we get this, which has 2 rewards in it, R0 and R1. And then we can expand it out k times and we get this formula where we have the first k rewards and then we cap it off with the value function k steps into the future. And these formulas just follow pretty directly from just looking at the formula for the Q function with this discounted sum. If you just account for all the reward terms in both, if you just try to account for all the reward terms and look at what kind of coefficient they should have, you'll see that these equalities hold. Okay, so that's the those are the Bellman equations that the Q function should satisfy, and we can also define this backup operator. And the backup operator is where you take the right-hand side of the Bellman equation, where you're looking into the future, and you just write it down as you consider an operator that acts on Q functions, where you replace you just take the old Q function and you substitute it in for where Q appears on the right-hand side of the Bellman equation. So this we can define this Bellman backup operator, which is called script T pi, acting on a Q function. So it just maps Q functions to Q functions, and this is how it's defined. As we talked about 2 classes ago, there's also another interpretation is that this is what you get if you do a finite horizon. If you have you can define this in terms of a certain finite horizon problem where you actually look ahead 2 steps, or you do 2 steps of backups in a finite horizon problem. So this is how we define this Bellman backup operator, and Q pi is a fixed point of the operator. That's just an equivalent statement of the Bellman equation. And if we apply it, since this Bellman operator is a contraction, if we apply it over and over again, the result, no matter what Q we start with, the result will converge to the fixed point, which is this Q pi. So I'm just kind of restating. These are the same kind of statements we made 2 classes ago when we were talking about value iteration and policy iteration. I'm just restating these for Q functions. and it's pretty straightforward to derive these in the same way that we derive these statements for value functions. So if you're confused about why these statements are true, you can just look at the derivation for value functions of why, like how the backup is defined and why this iteration, why this series converges for the value function v, and the same argument applies for q. Okay, so now we can talk about q star, which is the q function of the optimal policy. So let's let pi star denote the optimal policy according to in the gamma discounted for the gamma discounted return. So pi star is the optimal policy for the gamma discounted return, and q star is just defined as the q function of the optimal policy. And you can also think of that as the maximum overall policies of the q value for that state action pair. Because recall that the q value just means the expected return if you start with this state action pair. So the return is going to be maximized at that state action pair if and only if you execute an optimal policy for all subsequent time steps. So we can take this maximum over policy. We can say that the best possible q value you can get is obtained by taking the globally optimal policy. So it's also, by definition, it's going to be the argmax. The optimal policy is the argmax of the optimal q function, because the q function is telling you the expected returns, and to optimize. So the action you should take, the first action you should take is the action that gives you the best expected returns. So if we think of if we look at our Bellman equation for q pi, and we just look at what should this Bellman equation look like if we have the optimal policy, well, this expectation over actions turns into a max over actions. So this is what the Bellman equation looks like for the optimal q function. And another way to get this, maybe an easier way, is to just say that the q function it relates to the value function. The q function is just, the value function is just the expectation over actions of the q function. So if we write, this is this is conditioned on a sub 0. So if we write down the definition of the, let's see. Okay, I'll just say that this is another definition. This is another formula for the optimal q function. Yeah. So it's just the first reward plus the optimal value function at the next time step. Okay, so so we just talked about the backup operator for the. By the way, are any questions so far? If you're confused about some of these steps, please let me know, and I'll explain whichever ones you're confused about in more detail. All right. So we can also define a Bellman backup operator for q star. So this is just if we take the Bellman equation for q star and we write it down as we look at the right-hand side of the Bellman equation. So on the right-hand side, we've got this reward plus max of next q value. So if we just think of that as an operator where we substitute our q function into the right-hand side, that allows us to define this operator that acts on q functions, which is called the Bellman backup operator. So this is the Bellman backup operator for q functions, and q star is a fixed point of this operator. That's just a restatement of the Bellman equation for q star. And this operator happens to be a contraction, And if we apply it over and over again, the series converges to Q star, given any starting point. And I haven't derived this, but it follows from the same arguments that you can use to show that the Bellman backup is a contraction for V, and that when you keep the derivation we showed for value iteration, that when you keep applying this backup, you get to V star. Okay, so far we've just been laying out some of the properties of Q functions. And we've said that we have a Bellman equation. We can write down the Bellman equation for a fixed policy. And we can write down the Bellman equation that the optimal policy should satisfy. We can write down the Bellman equation that the optimal policy should satisfy. And there's also these two backup operators. There's the backup operator that converges to the optimal policy, and the backup operator that converges to the value function of the Q function of a fixed policy. So we've got our we've got Q pi, the value function of a fixed policy, Q star, the Q function of the optimal policy, and we've got the Q pi Bellman equation and a Q star Bellman equation, and we've got the backup that considers that this should be a fixed point of, the Q pi should be a fixed point of, and we've got the other backup operator that Q star should be a fixed point of. Okay, so now we can also define analogs of policy and iteration and value iteration that apply to Q functions instead of value functions. So these, so here we're just rewriting the previous policy iteration and value iteration algorithms in terms of Q functions. So usually, in practice, you wouldn't want to necessarily implement the algorithm this way, because it would require storing more numbers, since you have to store a Q function with all s times a values, as opposed to the state value function with just s values. But these are essentially the same algorithms we looked at 2 classes ago. So value iteration, remember, you just take the Bellman backup, you take this backup operator and you apply it over and over again. So the Q value iteration, this is what it looks like. You just iteratively apply the backup operator until it converges. Until some stopping condition is met, and the series will converge to Q star. And we can also write a policy iteration algorithm that involves Q functions, where each iteration, first we compute the greedy policy, which just means we take the argmax of the Q function, of the current Q function. Remember that the G operator there just means that you take the argmax over actions of the Q function at each state. And then after we update the policy, we take that policy pi n plus 1, and we compute the Q function for that policy. And this involves solving, to compute this Q function, we would have to solve some linear system of equations. That gives us our new Q function, and then we continue the iterations. And remember that this converges to the optimal policy and optimal Q function in a finite number of iterations. And we can also do the same kind of thing with modified policy iteration. So in modified policy iteration, instead of solving for the exact Q function of the policy, you apply a finite number of, you apply k Bellman backups using the backup operator t pi. So remember that if we apply this operator t pi if we apply it an infinite number of times, we get q pi. So this series, if we apply powers of t pi, we get a series that converges to q pi. If we apply a finite number of times, we get something that approximates q pi. So in modified policy iteration, we can just apply the backup operator k times for the policy evaluation step, which means the step where we're computing the value function of the policy. Okay, so that's modified policy iteration. So we went through these. So we had these three these three classic algorithms with Q functions. Any questions about that before I move on to sampling? Yeah.
Can you explain algorithm 2 again?
The policy iteration.
The second step, Q assignment. What is that?
Oh, this step.
Algorithm 2.
Oh, algorithm 2. Okay. Okay, yeah. So this. So I wrote that that q n plus 1, so that's the new q function we're trying to compute. We define that to equal the q function of the policy we just computed. So what that means is we find, okay, we've got this policy pi n plus 1, and then we just want to find the q function of that policy. So that means we want to find the q function that satisfies the Bellman equation. So we want to find a function satisfying q of SA equals expectation of action sampled according to pi of reward plus gamma times next q value. Oh, so actually, let me make this expectation a little more clear. So let me put in time indices. So we've got S0 and A0, and we've got expectation over S1 and A1. So Q of, we've got first reward 0 plus gamma times Q value of S1, A1. So we want to find a Q function that satisfies this Bellman equation. And this is a linear equation, because if you write it out with all the probabilities, you'll find that both sides are linear in Q. So you just solve this linear equation. I mean, what you would actually do in practice is, this linear equation, this is an equation in S times A variables, cardinality of the state space times the action space. And we don't want to solve a big system like that. So we would rather solve a system that has S variables in it instead. So what we could do instead is just write down the Bellman equation for the state value function, which looks like just we have an expectation over we have the same kind of expectation, but oops. Now we have reward 0 plus gamma times v of S1. So this is the Bellman equation that v pi should satisfy. And once we compute v pi, we can then compute q pi, because q pi of SA equals expectation of reward plus next value of plus v pi of S. So I'll put time indices on this to make it a little more clear. So if we've got v pi, we can compute q pi using this formula. So what you would actually do in practice to compute q pi in any kind of policy iteration algorithm is you would first solve the linear equation to get v pi, and then substitute that into the right-hand side here to get q pi. And in fact, on your homework assignment, you'll have to do exactly that. So you have an MDP where you're going to first compute the state value function, and then you're going to compute the q function from that. So that's, yeah, does that make sense? Okay. Okay, so now, so far, all we've done is we've recapped the policy iteration and value iteration, but with q functions. And we haven't accomplished anything because these are, the algorithms still have the same, they still have the same problem that the old ones had, which was that we can only apply these algorithms if we know all the transition probabilities. So if we want to compute expectations like this, we can only do it if we know what's the probability of state 1 given action 0 and state 0. So now what we're going to do is derive some algorithms that we can apply when we don't know the transition probabilities. So we're going to derive model-free algorithms. So let's first start off with the Bellman backup formulas. So we've got these two Bellman backup operators. That one of them is what we use to find q pi, and the other one is what we use to find q star. So if we can apply these formulas, then we're in good shape, because then we can estimate we can estimate q pi by applying t pi over and over again, and then we can do something like policy iteration. Or if we can approximate the Bellman operator, the t Bellman operator, then we can apply that operator over and over again, and we should converge to q star. So if we can approximate these operators somehow using samples, then we can apply policy iteration or value iteration. So the really nice thing about Q functions is we can write down an unbiased estimator for the right-hand side of these backup formulas. So notice that these backup formulas have an expectation over states. We can write down an unbiased estimator. I mean, if we just have one transition, one state transition, that gives us an unbiased estimator of the right-hand side of these formulas. And the nice thing about that is it turns out that, well, this formula, these estimators are unbiased even if we executed some different policy to collect the states and the actions. So I mean, we just, all we need to compute this right-hand side here is we need one state transition. We need S0, A0, R0, S1. We don't need A1 because we're taking the expectation over that. So we don't care. A1, we don't care what policy, what you actually did at time step 1, what action you actually took, because we have an expectation over A1. So we can compute the right-hand side of these formulas without, I mean, it doesn't matter what policy we actually executed for computing the right-hand side of these formulas, as long as we had S0 and A0. Does that make sense? Yeah.
So the policy, I guess the reason why we can compute that is because the policy is something we're going to parameterize. Is that correct? Why we can compute the expectation over A1 sample from pi?
Oh, yes. Yeah, that's right. So the policy is something that we're approximating, or the policy is something that's updated as part of our algorithm. Yeah, so we have pi, and we can just compute this expectation using the pi that we're storing. Yeah, that's right. So it doesn't matter if we actually took some different action at time step 1, because we're taking the expectation. So we'll see this in several other ways. So if we were to just apply, actually ignore that last bullet point. Same thing, we can also approximate the k times iterated backup operator. So if we just write down, okay, this is the formula we've seen many times. This is the definition of the Bellman backup. So we can also just take Q on the right-hand side and substitute in TQ, or T pi applied to Q. So I mean, we want to find, we want to see what happens when you apply T pi twice. So we just take T and we apply it to T. I mean, we take T pi and we apply it to T pi Q. So we substitute that into the right-hand side here, and we get like a 2-time step expanded version of the formula. And we can do that k times, and we get this k times expanded formula where we have k rewards and then Q function k time steps later. So this means, so we can also write down an unbiased estimator for this k times applied backup operator. So if we have a trajectory, so if we have a trajectory segment, S0, A0, R0, and so on up until Sk, then we can we can construct this expression on the right-hand side, and that gives us an unbiased estimator of the k times applied Bellman operator. So if we wanted to do a version of modified policy iteration, that's where we don't do the backup exactly, but we do it approximately instead, then we could use this formula to do it, where we just have to collect your trajectory, and that trajectory gives us a estimator of the this backed up Q value. We're not going to use that right away, but that's going to turn out to be important later when we talk about the SARSA algorithm, which is one of the popular algorithms that you can use to learn a Q function. Okay, so let's just do a last. I mean, compare the backups that we got for Q functions and for the state value functions V. And the point here is, so why are we using Q functions instead of V functions? So our goal today is to get a model-free algorithm, a model-free version of value iteration and policy iteration. So why are we using Q functions instead of value functions? So let's compare the backup operators. With the Q function backup, we have expectation over S, over the state, and then expectation over actions inside. Or we have the expectation over states on the on the outside, and we have the actions on the inside. The expectation or the max over actions on the inside. Whereas for the value functions, it's the other way around. We have the expectation or max over actions on the outside, and we have the state transition on the inside. And so that's the big difference between the two kinds of value of Bellman backups. And the thing is, we can get an unbiased estimate for the right-hand side of these Q function expressions by taking one state transition. But we can't get an unbiased estimate of these formulas by taking one state transition. Actually, that's not true. For this one, we can. This one, we can get an unbiased estimator by taking one state transition, but not this one. Because if we take a max, the max of the expectation is not equal to the expectation of the max. So this is sort of, if you try to think about how you might do these backup formulas for the value function, if you don't know the transition probabilities and you only get to see a trajectory, then it doesn't work out for the value functions, but it does work out for the Q functions that you can get unbiased estimators. So another way to think about this is note that for the you don't get to go back to a given state. So you only get to see the assumption here is we get a trajectory of states and actions and rewards, and we don't get to write down. We don't get to see many transitions that start with a given state. We only get to see one transition, and we want to construct an estimator for the backed up value using that one transition. So it doesn't work for the value functions, but it does work. It doesn't work for the V functions, but it does work for the Q functions. So that's why we're going to use Q functions to get model-free algorithms. Okay. There are also a couple of other benefits of using Q functions. The other thing is we can directly compute the greedy action using the Q function. So a Q function implicitly defines a policy without knowing anything about the transition probabilities. Whereas if we just have a V function, then that doesn't necessarily, that doesn't directly define a policy unless we have some other way of maximizing over actions. So if we know the transition probabilities, then we can use that value function to define a Q function, and then we're fine. But if we don't know them, then it's not clear how we get a policy out of our value function. And as I said on the previous slide, we can compute an unbiased estimator of the backup value using a single transition. And the other thing is we can compute an unbiased estimator of the backup value using off-policy data, meaning data that you collected by running another policy other than pi. So that's because, as I said, the you can get this unbiased estimator regardless of what policy you actually use to collect the data. The estimator that you get for the backed up Q value doesn't depend on what policy you are running. So those are the nice properties of Q. So now what we can do is to continue deriving model-free algorithms. What we're going to do is we're going to start off with Q value iteration or Q policy iteration, and we're going to replace the backup step by the estimator. We're going to replace the backed up Q value by an unbiased estimator of the backed up Q value. So what we want to do is we want to apply this backup operator T to Q, but what we can do instead is we can take this expression on the right-hand side here, which is an unbiased estimator of T applied to Q. So we're just going to collect a trajectory of state action. So we've got state 0, state 1, state 2, and so on. We just run our policy to get a trajectory, and then we can construct unbiased estimator of the Q function at every state action pair along that trajectory. So that's how our algorithms are going to look. Does that make sense, the basic setup? Like we're going to just sample, we're going to run our policy, collect some data, and then try to compute the backed up Q values using that data. We're going to try to compute an approximate version of the Bellman backup operator using our data. So I'll just make that a little bit more explicit. So this is what the algorithm looks like for Q value iteration, where you don't know any of the transition probabilities and you're just sampling from the system. So each iteration, you interact with the environment for a while, for let's say capital K time steps, and then we're going to update the Q value at every state action pair. And the way we update it is we look at all the times you visited that state action pair. So we're taking all T's, all time steps T such that you visit that state action pair, and we take the mean of the backed up Q value at that time step. And here, the backed up Q value is just defined as reward plus next Q, where we took a max over the next action. And note that this doesn't depend on what action you actually took at time step A sub T plus 1. So it doesn't actually matter. So the backed up Q values that we're going to get don't depend on what policy we use to interact with the environment. And so this is our iteration, and we just keep on doing that over and over again. And what's happening each iteration is our new Q value, our new Q function equals our old Q function with the Bellman backup operator applied, plus some noise. Because we're doing a finite number of samples, so there's always going to be some noise. We're not going to do the backup perfectly because we're not like integrating, or we're not like summing over all the probabilities properly. We're just doing a Monte Carlo estimate everywhere. So this is what we're effectively doing. And it might not be clear that this will actually converge, because maybe we're almost doing the right thing the value iteration is trying to do, but we're adding noise, so maybe we're getting worse and worse each time. So we're going to answer that in the next few slides, why this actually works. If you do it right, this can actually be made to work and to still converge to Q star.
Do you have to sample all the states and action pairs?
If you want this to converge, you will have to sample all the states and state action pairs. If you, I mean, this algorithm makes sense even if you aren't sampling all the state action pairs. I guess you would have to define what the what you do for a state action pair that you never visited. But we could define something sensible, like you keep the Q value the same if you don't, if you never visited that state action pair. To answer your question, this will only really make sense if you visit every state action pair. This is just going to be for didactic purposes anyway, though. We're going to move on. Like you'll see, hopefully your question will be answered pretty soon. Okay, so that was one way of writing out this value iteration where you're only allowed to do sampling. But we can write it out in a different way, which is also going to be insightful. So previously we defined our Q value as the average of the backed up Q values for all visits to that state action pair. So what we can do is, we can note that if you have a bunch of random variables, you can rewrite the mean of those random variables as just the minimum of the squared distance from, we can write it as the minimizer of this sum of squared distances. So if you have the sum of squared distances, the value of x that minimizes this is just the average. So applying that to the Q values, you see that we can write our formula here where we take the average of all the backed up Q values. We can rewrite that as just the minimum of the here we're taking the minimum of Q of SA, this one scalar. I should have written Q of SA here. So minimum of over Q of SA of this sum of squared errors. And similarly, we can write down the update to the whole Q function. So we can write down the new Q function as just the argmin over all Q functions of the sum of squared errors of the estimator of the backed up Q value minus our Q value. So we're trying to find the Q function that minimizes the squared error to all the backed up Q values. So now just rewriting the previous algorithm, except using this least squares version, it looks like this, where we say the backed up Q value is just, you take the argmin over Q functions of the squared error at all states. This formula is also doing the same thing. It's taking the backup operator, and there's a little bit of noise. So that's one way to think about this Bellman backup operation, or how to rewrite Q value iteration. Now we need to do another. We can consider another variation on this algorithm. So let's say in the previous slide we were trying to do a backup where we take the Q value and we replace it by this estimate of the Q value, this TQ hat, which is just the estimator of the Q value. But maybe that's really noisy. So even though it has the right expectation, since there's so much noise, our Q value is going to get worse if we just apply this thing. So what we can do instead is just move a little bit in that direction. We can set our new Q value to be a small epsilon times the backed up Q value estimate plus 1 minus epsilon times the current value. So that way we're only updating it by a little. So is that a good idea? Well, it's actually the same thing as just taking the squared error and taking a little gradient step on that squared error with step size epsilon. So if we just think about the squared error and we update Q by doing a little gradient step, well, the gradient is just Q minus the backed up value. And when we just apply that, we get 1 minus epsilon times the old Q function plus epsilon times the new Q function. So as you probably know, if you take a small gradient step, or if you take a small noisy gradient step, or a small multiple of a noisy gradient estimate, then your function value improves in expectation. So if we make epsilon small enough, the expected value of our error objective is going to decrease. So this is like SGD. If you have SGD, then if your step size is too big, you might just get worse if the noise is bigger than the signal. But if you make your step size small enough, then you're guaranteed to get better if you take an SGD step. Okay, so now we can do a version of the previous algorithm where we do a partial update instead of the full update. So if we do that, so we interact with the environment for k time steps, and then we take a little gradient step on the Bellman error. So we write down our squared error, and we take a little gradient step on it. And another way to write that is we, instead of just thinking about taking a gradient step, you can recognize that this is exactly the same as taking the minimum over Q functions of a adjusted version of the Q value. So you take the old Q value plus epsilon times a noisy version of the Q value, new Q value, and if we oh, whoops, this should say what should this say? This should say minus Q here, argument of this thing minus Q squared. So we're taking an estimator of the new Q value where you interpolate between the old value and the noisy estimate of the current new value, and you want that to be you want Q to be close to that. So just pretend I have a minus Q inside the norm here. Okay, in the description of the algorithm here, I said that you interact with the environment for k time steps. But you can do this update after any number of time steps you want. So you could just do one time step and then update the Q function after each time step. So you update the Q function. You see one state transition, and you update the Q function to reduce the Bellman error a little bit on that state transition, or to move the Q function a little bit towards the backed up value of the Q function. So this algorithm is called Watkins Q learning. This was actually a pretty like a breakthrough paper back in 1992, because it's a model-free reinforcement learning algorithm that's guaranteed to converge to the optimal policy. So previously, people hadn't, as far as I know, people hadn't shown that there was some model-free algorithm that would converge to the optimal policy. Maybe they had, but yeah, I don't think so. And so this ends up, it's a pretty simple algorithm. You have to be careful about the the schedule of the step sizes. So you can't just choose a fixed epsilon and leave it the same for all time. Epsilon has to decrease over time to make sure you converge. You also need a condition like, so the condition that needs to hold is that you visit every state action pair infinitely often. So you need to be a little careful about some conditions, like visiting every state action pair infinitely often and choosing the right step size schedule. But if you do that, then if you just apply this algorithm, as n goes to infinity, you converge to Q star, the optimal Q function. So that's the k equals 1 case. Large K, this is sort of a batch Q value iteration algorithm. So you might have heard of the DQN algorithm, the deep Q learning algorithm, which was published a few years ago, and you're going to implement it on your next homework assignment. So that algorithm is actually a lot like this batch Q value iteration. Yeah, that's a lot like batch Q value iteration, because you, though it's implemented in a using SGD to do this argument. So we'll talk about the connection later in the next class, where I'll talk more about DQN. But it turns out that DQN, even though it's called deep Q learning usually, it's actually more similar to this Q value iteration algorithm here. Okay, so does it converge? I said that the Watkins, this classic Watkins paper showed that it converges. I'm not going to go through the convergence proof. But let's just try to get a little intuition for it. So here's what our partial backup looks like. Our new Q value, which equals the old Q value plus epsilon times this gradient, times the gradient of the Bellman error with respect to Q. So, or the gradient of backed up Q value minus current Q value. So this is, and there's noise because we're not actually using the backed up Q value exactly. We're using an unbiased estimator of it. So this is the update we're doing each step. Does this just nicely converge? I mean, because it seems like we're just doing gradient descent on this objective right here. Well, we're not exactly, unfortunately, that's not exactly what we're doing because this quantity q is changing. So if this q value in here were fixed, then we would just be doing gradient descent on our loss function here. But this thing is changing, so it's like we're chasing after a moving target. Like here we've got q, and we've got tq, and q is chasing after tq, but it's always running away. So it's not totally obvious that it's going to converge. But it turns out that it does converge under appropriate conditions. So there's a general result in this, and actually the paper, I mean, the original convergence proof is from that Watkins paper, but that's a kind of long, complicated proof. But actually, there's a really nice proof of this in this paper by Jacqueline, Jordan, and Singh on the convergence of stochastic iterative dynamic programming algorithms. So they provide a pretty general result, which is used to prove a lot of these convergence results. So it says that because if you have any kind of contraction and you do, well, this isn't exactly what the result says, but this is what the result implies. So if you have a contraction and you do a partial version of that contraction, meaning you do epsilon times the contraction operator plus 1 minus epsilon times your old value, and you have a noisy estimate of the contracted value, then this will converge to the fixed point of the contraction. So they have a general result that says if you have that shows that if you can do a noisy version of a contraction, or if you have a noisy contraction update and you do a partial version of it, or you interpolate between your current value and the new value, then this will converge. So if you want to see exactly what they prove, then I recommend looking at the paper. But that result is used to prove the convergence of this. That can be used to prove the convergence of Watkins Q-learning as well as a lot of other algorithms, a lot of other online reinforcement learning algorithms. And you have to be really careful about step sizes, though, and step size schedules, though. So you have to, it's like, you might have seen some of these results on SGD convergence, for example. You have the same kind of thing where you have to make sure that your sum of step sizes adds up to infinity, but the sum of step sizes squared adds up to a finite number. So that's satisfied, for example, by taking step size equals 1 over time step. So if you do that, then it's going to converge. OK, and we're not going to, so next class we're going to talk all about function approximation. So we're going to talk about deep learning tomorrow, Monday. But for now, I just want to say a little bit about it so I can justify to you why I just went through that whole series of different versions of the same algorithm. The point of all of that was to be able to do value iteration in a more general setting, or a setting where we have less information, less knowledge about the system. So we want to be able to do value iteration where we don't know what the transition probabilities are. So first we had to switch over to Q functions because that let us do a get an unbiased estimate of the backed up Q value, whereas we couldn't do that for the backed up V. So we switched over to Q functions. Then we derived this Q value iteration algorithm, which you can do with sampling. And then we rewrote it a bunch of times to have gradients, to do gradients updates on the Bellman error, or minimize the squared Bellman error, instead of just saying that we set some Q value to so-and-so. So we rewrote our algorithm a bunch of times so that it looked like we're minimizing some error each iteration. So now, after we did all that work, now we have an algorithm where we can substitute in a function approximator for the Q function. and we have an algorithm that actually makes sense with function approximation. So what we do is now we have, let's say now we have an infinite state space, or we have like images. Our state is, instead of a state, we have an image that's going to be input to our Q function. Now we can, and so we don't want to have a Q function, which is a table of values for every state action pair. But now we can just have a big neural network, which approximates our Q function. So now what we can do is our update step was just you write down this Bellman error, this Q minus backed up Q. We can just write down the Bellman error, and we can do a nonlinear. It's nonlinear least squares, or nonlinear minimization of this Bellman error. So we could either do one gradient update on that, or we could do many gradient steps on that. And that's exactly, this is called neural fitted Q iteration. You sample a bunch of trajectories using your current policy, which is usually defined as the greedy policy for your current Q function plus some exploration noise. For example, epsilon greedy, where you sample a random action with probability epsilon. So you sample your trajectory using your policy, and then you update the parameters of your Q function by solving this nonlinear least squares. So that's neural fitted Q iteration. We're going to also talk about a more online version of this called DQN, or the Deep Q Network algorithm, next class, and several variations of that algorithm. It's worth noting that when you have a table of Q values, then you actually have a lot of nice convergence results. When you use function approximation, you don't have any convergence results, unfortunately. Or you do if you're under very special conditions of what kind of function approximator you use. But actually, it's very hard to get a convergence result for a value iteration with function approximation. So in practice, we have to kind of give up on convergence results when we move over to function approximation. Maybe not. Maybe someone will discover I don't know, some new really nice theory that lets you use flexible function approximation and make it converge. I don't know. Give it a try if that's what you're interested in. But right now, there isn't that much in the way of. You can't say that much about convergence when you have an arbitrary nonlinear function approximator, and you're doing some algorithm like this. So that's a little bit unfortunate, but yeah, maybe maybe that situation will improve. I don't know.
So here, the policy pi n, this is like all policy, so you can use any policy in that step?
Yeah. So yeah, you can use any policy in that step, and it'll sort of make sense in that you get an unbiased estimate of the backed up Q value. In practice, the policy you use, it does matter a lot what policy you use when you have function approximation, because when you have function approximation, you can't express an arbitrary Q function. You just have some space of Q functions that you know how to express. So the policy you use is going to determine the density over state action space that you're exploring. And that means you're going to use your capacity in certain parts of the state action space, but not others. So if you're not careful if you just choose any old policy and you don't do that in a consistent way, it's just you're going to kind of thrash around and try to approximate different stuff. So one iteration, you're going to try to get a good fit in one part of state space, and another iteration, you're going to try to get a good fit somewhere else. So actually, in practice, it depends really heavily on what kind of policy you use, and it's important that you have some stable policy that doesn't change too fast. Well, I don't know. It's actually not that clear what it depends on, but in practice, yeah, it matters.
So would it be possible to define like the pi n as like this sort of like the argmax of your Q theta at that point in time, or would that not be a good idea?
Yeah, so that's actually what you're supposed to do in this algorithm. So usually you define it as the greedy policy plus some noise somehow. So you could say you could say pi n of A given S equals, so we're going to say argmax over, let me erase some of this other stuff. So argmax of Qn with probability 1 minus epsilon, and we're going to define it as some uniform random action with probability epsilon. So that's an epsilon greedy policy. So that's a typical choice. If you have a continuous state and action space, you can also implement this algorithm, and then you don't want to take a uniform sample over you don't necessarily want to sample a uniform action from the space of all valid actions, but maybe you'll have a Gaussian distribution or something. So, okay, that's it for today on the slides. Does anyone have questions? Okay, if I'll be doing office hours after this. Sergey, what room is it in today?
7:30, Siddhartha Dai Hall.
Okay, so it's in the Newton room in Siddhartha Dai Hall, 7:30. If you haven't signed up, you can still come anyway. And I'll see you on Monday.
So I'm looking forward to seeing whether my guinea pig can actually do the assignment.
Yeah, that'll be nice.
It's Abhishek, so I think
Okay.
if